Welcome to Analytical Chemistry Vision, a platform dedicated to exploring the theoretical and experimental aspects of chemistry, blending classroom learning with laboratory research to enhance understanding and inspire innovation in chemical science. Let us start interesting and highly useful topic for UG, PG, and research students, that is gravimetric analysis. This is classical method, which is very simple, low cost, easy accessible, and no special training is needed, applied for quantitative determination of variety of real samples. In this lecture, we will learn following topics in gravimetric analysis. First one is what is gravimetric analysis. Second one is conditions of precipitation. Third one is solubility and solubility product. Fourth one is terms such as co-precipitation, post-precipitation, supersaturation, and peptization. Fifth one is steps involved in gravimetric analysis of barium as a barium sulfate. And sixth one is numerical problems based on solubility and solubility product. Let us know, what is gravimetric analysis? Gravimetric analysis is a classical quantitative analytical technique in which the amount of an analyte is determined by measuring mass. The analyte is converted into a pure, stable, and weighable solid through precipitation, filtration, drying, ignition, and weighing. The mass of this final product is used to calculate the amount of the target substance based on known stoichiometry. In this gravimetric analysis, the precipitation is very important parameters, which can be defined as precipitation is a chemical process in which dissolved ions in a solution combine to form an insoluble solid called a precipitate. This solid separates out because its solubility limit is exceeded. Example, if you mix silver nitrate, AgNO3, with sodium chloride, NaCl, the ions Ag plus ion and Cl minus ion react to form an insoluble white solid silver chloride, AgCl, which is given below. Next, here we will see, what is solubility? Solubility refers to the maximum amount of a substance, solute, that can dissolve in a given amount of solvent at a specific temperature and pressure. It indicates how much solute can form a stable, homogeneous solution. First one is, 36 gram of NaCl is dissolved in 100 gram of water at 25 centigrade. This means NaCl is highly soluble in water. Second one is, 0.2 gram CaSO4 is dissolved in 100 milliliter of water at room temperature, means the substance is sprangly soluble. Third one is, 0.0002 gram of AgCl is dissolved in 100 milliliter of water. Hence, it is considered to be insoluble and forms a precipitate. Further, we should know, solubility product, KSP, solubility product, is the equilibrium constant for the dissolution of a sparingly soluble ionic solid in water. When salt AB is dissolved, it ionizes into A plus ion and B minus ion. And thus the solubility product KSP is the product of A plus ion into B minus ion, where the KSP is constant at a given temperature and indicates how much of the salt can dissolve. Here, we understand the relationship between ionic product and solubility product which control the precipitate formation. Where the ionic product, IP, can be defined as the product of the actual concentrations of ions present in a solution at a given moment, each raised to the power of its stoichiometric coefficient in the dissociation equation. General expression for ionic product is, for a salt, AMBN is dissociated in aqueous solution, and at the equilibrium condition is M into A to the power AN plus, and N into B to the power M minus. Thus, the ionic product is product of the A to the power N plus, whole to the power M multiplied by B to power M minus, and whole to the power N. Here, we will know the condition for precipitation of substance in solution. First condition is, if IP is less than KSP, then solution is unsaturated, no precipitation. Second one is, IP is equal to KSP, then solution is saturated, equilibrium. Third one is, IP is greater than KSP, then solution is supersaturated, precipitation occurs. For example, the precipitation of silver chloride, salt AgCl is dissociated into Ag plus ion and Cl minus ion in solution. And if concentration of Ag plus ion is 1 into 10 to the power minus 3 molar, and Cl ion is 2 into 10 to the power minus 3 molar, the ionic product, IP, will be finally 2 into 10 to power minus 6. However, the Ksp for AgCl is 1.8 into 10 to power minus 10. Thus, the IP is less than Ks. P. The solution is supersaturated and AgCl will precipitate. Based on the previous slide, we can draw the graph that illustrates how the ionic product, IP, controls dissolution and precipitation. When IP exceeds Ksp, excess ions precipitate as solid. When IP is less than Ksp, the solid dissolves. At IP equal to Ksp, the system is at dynamic equilibrium with no net change in solubility. This chart illustrates precipitation from a supersaturated solution over time. At high supersaturation, rapid nucleation occurs, forming many small particles. As concentration decreases toward saturated solubility, nucleation slows and crystal growth dominates, producing fewer but larger, purer crystals, an essential principle in controlled gravimetric precipitation. Here we will know what are conditions, factors that affect the precipitation. First one is low supersaturation. Precipitation must occur under low supersaturation to promote formation of large, pure, and easily filterable crystals rather than fine colloidal particles. Second one is slow addition of reagent. The precipitating reagent should be added slowly with continuous stirring to avoid localized high concentration zones that produce impure precipitates. Third one is dilute solutions. Using dilute analyte and reagent solutions reduces rapid nucleation and favors controlled crystal growth, improving purity and particle size. Fourth one is temperature control. Carrying out precipitation at elevated temperature enhances solubility, reduces co-precipitation, and allows formation of larger crystals. Next here we will see more conditions. Fifth one is pH optimization. The pH of the solution must be adjusted to ensure selective precipitation of the analyte without interference from other ions. Sixth one is digestion of precipitate. Allowing the precipitate to stand in hot solution helps small particles dissolve and redeposit onto larger ones, Oswald ripening, improving filterability. Seventh one is avoiding excess reagent. Excess precipitating agent can lead to adsorption of impurities and contamination of the final precipitate. Eighth one is proper washing. Washing with suitable dilute electrolyte removes trapped impurities without dissolving the precipitate. Here we will learn what are the impurities that carried out during the precipitation process. First one is co-precipitation, where the co-precipitation is a process in which impurities get carried down along with the desired precipitate during gravimetric analysis. Even though these interfering ions are normally soluble, they become incorporated into the precipitate because of physical or chemical interactions. Let us know what are the different types of co-precipitation. First one is surface adsorption, where impurity ions get adsorbed on the surface of the growing precipitate particles. Common in colloidal or finely divided precipitates. Example, BaSO4 adsorbing Na plus ion or Cl minus ion. Second one is occlusion, where impurities get trapped inside the crystal lattice during rapid crystal growth. Occurs when precipitate forms too quickly, leads to mechanical entrapment of foreign ions. Now, we will see third type of co-precipitation, that is inclusion, isomorphous replacement. Here, an impurity ion of similar size and charge replaces the main ion in the crystal lattice. Example, Sr2 plus ion and Pb2 plus ion replace the Ba2 plus ion from BaSO4. Then, next is how to minimize co-precipitation. Slow precipitation by adding reagent dropwise. Use hot, dilute solutions. Digest the precipitate to allow recrystallization. Wash carefully with suitable wash liquids. Second type of impurity in precipitation process is post-precipitation. Post-precipitation is the process in which a second, unwanted precipitate forms after the primary precipitate has already formed. This occurs when the solution still contains ions capable of forming a more insoluble compound over time. Example, in gravimetric determination of barium as BaSO4, if the solution is left standing, strontium sulfate or calcium sulfate may slowly form and get deposited on BaSO4. Here understand how to prevent post-precipitation. For this, filter the precipitate immediately after digestion. Keep the solution hot to reduce formation of secondary precipitates. Maintain proper acidity to prevent unwanted hydrolysis products. Use a washing solution that prevents further precipitation. Another important parameter is supersaturation. Supersaturation is a condition in which a solution contains a higher concentration of dissolved solute than it can normally hold at a given temperature. It is a metastable state, meaning the solution is temporarily stable but can rapidly form a precipitate when disturbed. In gravimetry, high supersaturation leads to rapid formation of many tiny crystals, causing colloidal precipitates, poor filterability, and increased co-precipitation errors. Peptization is another process that occurred during the precipitation. Peptization is the process in which a freshly formed precipitate reverts into a stable colloidal state when washed with pure water or an inappropriate washing medium. This occurs because adsorbed ions on the precipitate surface form electric double layers, increasing repulsion and preventing particles from aggregating into a filterable solid. Example of peptization is, first one is ferric hydroxide precipitate. When washed with pure water, FeOH3 breaks into reddish-brown colloidal particles due to removal of electrolytes. Classic example of peptization. Second one is silver chloride precipitate. Washing AgCl with pure water removes adsorbed chloride ions, causing AgCl to disperse into a colloidal form. Here, we understand what are the criteria of selection of liquid wash. First one is, should not dissolve the precipitate. The wash liquid must have very low solubility for the precipitate to prevent loss of analyte. Second one is, should remove adsorbed impurities. It must effectively remove surface adsorbed ions and occluded impurities. Third one is, contains a common ion. A dilute electrolyte with a common ion, example, dilute BaCl2, for BaSO4, prevents peptization and dissolution. Further, fourth one is, prevents peptization of colloids, especially important for gelatinous precipitates, example, FeOH3. Fifth one is, does not react chemically. The wash liquid should not form soluble complexes or new precipitates with the analyte. Sixth one is, easy to remove on drying, ignition, leaves no residue after drying or ignition. Seventh one is, free from contaminating impurities, should be pure and of analytical grade. Let us learn gravimetric determination of barium as barium sulfate, BaSO4. Principle is, barium is quantitatively precipitated as insoluble barium sulfate by adding sulfate ions. The purified, dried precipitate is weighed, and barium content is calculated using stoichiometry. Reagents required are, first one is 5% barium chloride. This solution is prepared by dissolving 5 grams of substance in 100 ml distilled water. Second one is 0.2 molar potassium sulfate, K2S4. This solution is prepared by dissolving 3.49 grams of substance in 100 ml distilled water. Here we will see the gravimetric determination of barium as barium sulfate. First step is, prepare sample solution. Transfer a measured 100 ml of the barium containing solution into a 250 ml of beaker. Second step is, heat the solution. Place the flask on a hot plate or in a boiling water bath and heat to near boiling, not vigorous bumping. Further, third step is, desulfate reagent slowly. While the solution is near boiling and with stirring, add the sulfate, H2SO4, reagent dropwise, or very slowly, to avoid local supersaturation. Continue until a slight excess of sulfate is present, that is, a few drops extra after no further cloudiness forms. Fourth step is, digest the precipitate, aging. Maintain the hot solution, just below boiling, and allow the precipitate to digest for 20 to 60 minutes, gentle heating with occasional gentle swirling. This promotes crystal growth and purer, filterable BaSO4. Fifth step is, filter the precipitate, collect the BaSO4. By filtration using a pre-weighed, ignited porcelain crucible or a gouge crucible, or by gravity filtration through ashless filter paper and transfer to a crucible. If using filter paper, transfer carefully by rinsing. Sixth step is, wash the precipitate. Wash the precipitate on the filter with hot distilled water repeatedly to remove soluble impurities, chlorides, sulfates of alkali, etc. Final washes may include small volumes of ethanol, acetone to aid drying. Do not use alcohol if it will dissolve any entrapped impurities you worry about. Next, seventh one is, dry. Ignite to constant mass. Transfer precipitate, if on filter paper, to a weighed crucible. Ignite at burner or put in a muffle furnace at 500 to 700 centigrade for 15 minutes to 30 minutes to remove volatile matter and obtain constant mass. BaS4 is thermally stable, so ignition does not decompose it. The goal is constant, dry mass. Eighth one is, cool in desiccator and weigh. Cool the crucible in a desiccator to room temperature and weigh accurately. Repeat drying, ignition, cooling and weighing until 2 successive weighings agree, constant mass. Finally, here we'll see the calculation for determination of barium as barium sulfate. As in this experiments, 100 ml of 5% barium chloride is precipitated with 100 ml of 0.2 molar potassium sulfate. Calculate the barium as barium sulfate. First step is, amount of BaCl2. 5% means, 5 gram 5 BaCl2. In 100 ml solution or molar mass of BaCl 208.23 gram. And then, moles of barium chloride will be equal to 5 divided by 208.23. Which is equal to 0.0240 mole. Second step is, amount of potassium sulfate. Moles of potassium sulfate is equal to molar mass, 0.2, into volume of solution, 0.1, which is equal to 0.02. Third step is, limiting reagent, stoichiometric ratio is 1:1. Then the concentration of barium chloride will be 0.024 mole and or potassium sulfate will be 0.02 moles. Fourth step is, mass of barium sulfate formed. Molar mass of barium sulfate is 233.39 gram and mass of barium sulfate will be 0.02 into 233.39, and finally 4.67 gram of barium sulfate will be precipitated as Ba. Let us learn some numerical problems based on solubility and solubility product. First problem is, the solubility of AgCl in water at 25 centigrade is 1.3 into 10 to the power minus 5 moles. Calculate its Ksp. Solution for this question is given here. As we know that Ksp for AgCl is square of S square, which is molar solubility of the salt. And finally, the Ksp for AgCl is 1.69 into 10 to the power minus 10. Second problem is, the solubility product of BaSO4 is 1.1 into 10 to the power minus 10. Calculate its molar solubility in water. Solution is given here, as we know that Ksp is square of the molar solubility of the salt. And finally answer is 1.05 into 10 to the power minus 5 molar. Next, third problem is, calculate solubility of AgCl in 0.1 molar NaCl solution is given here. As we know the Ksp is 1.8 into 10 to power minus 10. And we know that Ksp is ionic product of Ag plus ion and Cl minus ion. And finally the solubility of AgCl is 1.8 into 10 to the power minus 9 molar. Fourth question is, will AgCl precipitate when 10 ml of 0.01 molar silver nitrate is mixed with 10 ml of 0.01 molar NaCl? Solution is given here. We know Ksp of AgCl, which is 1.8 into 10 to the power minus 10. Further, the actual concentration of Ag plus ion and Cl minus ion in 20 ml of solution will be 0.0005 molar. Then, ionic product, Ip, of both ion will be 2.5 into 10 to the power minus 5. Thus, Ip is greater than Ksp, and result the precipitation take place. Next, fifth question is, calculate solubility of BaSO4 in 0.2 molar Na2SO4. The solubility product of BaSO4 is 1.1 into 10 to the power minus 10. The solubility will be calculated by dividing the value of Ksp by 0.02. The answer will be 5.5 into 10 to the power minus 9 molar. Next, sixth question is, does precipitation of AgCl will occur? If the concentration of Ag plus ion is 1 into 10 to the power minus 3, and concentration of Cl minus ion is 1 into 10 to the power minus 6, the Ip will be 1 into 10 to the power minus 9, which is less than the solubility product of AgCl. The precipitation will occur. Here, there are other application of gravimetric analysis for quantitative determination of chloride, sulfate, nickel, lead, calcium using different precipitating reagents given in second column of the table, and analyte can be determined from water, food, biological fluids, alloy, steel, milk, industrial wastewater samples. In addition, more analytes such as magnesium, barium, iron, silica using different precipitating agent in second column of the table, used for analysis of pharmaceuticals, cement, ores, soil, rocks, etc. Here we can see the reference books that are used for making this video lecture. Thus, in summary, this lecture explains the principles and practice of gravimetric analysis, including precipitation conditions, solubility concepts, impurities, and numerical problems. The method is simple, economical, accurate, and accessible, requiring no sophisticated instruments or special training. It is widely applicable to environmental, pharmaceutical, food, and industrial samples, making it suitable for UG, PG, and research-level analytical studies. Thank you for watching the Analytical Chemistry Vision. If you like this video, please visit our channel for more interesting theoretical and experimental lectures. Don't forget to like, share, and subscribe, and share your feedback in the comments to help us improve further. Thank you.